Assalamualaikum warahmatullahi wabarakatuh. We proceed with part 2 in polymer structure chapter. Okay, for step growth polymerization, it consists of two or more monomers joining together with the elimination of a small molecule such as water, alcohol, and so on. And the monomer must have different reactive functional groups so that they can react together to form a polymer. So means that you have a monomer A and monomer B that will react to form a polymer. So in any reaction resulting in the formation of a chain or network of high molar mass, the functionality of the monomer is of prime importance in the step growth polymerization. So a linear chain of the monomer residues is obtained by the stepwise intermolecular condensation or addition of the reactive groups in bifunctional monomers. So as we can see in the diagram below, we have monomer 1 consists of hydroxyl group and hydrogen bond will react with the monomer 2 consists of the same functional group, and then it will tend to produce a copolymer consists of OH and hydrogen bond. So H2O and H2O is the byproduct or the residue that will be eliminated during the end of the reaction. One is an overview of the polymerization process by addition and condensation. We look at the addition polymerization first. The properties of addition polymerization, it is contain monomer with double bond, while for condensation polymerization, it contains monomer with different functional group. And addition is repeating units joined together by covalent bond without loss of any molecule, while in the condensation, the repeating unit joined together by covalent bonds with a loss of water and HCl molecule and etc. Now we look at the scheme here. The monomer will undergo polymerization process to form a polymer, and in addition polymerization, the monomer must consist of double bond or triple bond. For condensation polymerization, it has two monomer which consists of either same or different functionality. Okay, for this structure, we can see that they have a diol structure with the diol structure here and carboxylic acid, right, to produce an ester group, ester polyester. An example of condensation polymer are nylon, PET, while for the addition polymerization, the example are PE, PP, PS, and so on. I'm sure you are familiar with the addition and addition polymerization and step growth polymerization. This one is the ethane monomer, which has made by the addition polymerization. And we can see the label at the bottom of the bottle. For number 1 is referring to PET, number 2 HDPE, and so on. So widely used is PP, which is number 5. And if you look at the polystyrene label, it is number 6. Right? And this one is the propene monomer produced by the addition polymerization. We look at the structure composed of the double bond and undergo the polymerization process. The double bond will be released to produce a polypropylene to form, and it is single bond form with 1,000 repeating units. So some example of others monomer. This one is the illustration for the addition polymerization of polyethylene, polychlorine, PP, and Ptfe. So as we can see here, the monomer consists of double bond, and there is no loss of molecule at the end of the reaction, and long chain form, and the double bond, which is unsaturated monomer, it will produce the end of the product, it will tend to produce a saturated polymer consists of single bond, so it has no byproduct form. While for the condensation reaction, as we can see that the production of the byproduct, which is water here, is an example of the elimination of the water in the polyester. I mentioned earlier, for condensation polymerization must consist of at least two monomer. So as we can see, the first monomer we call as ethane 1,2-diol. So in ethane 1,2-diol, it consists of two hydroxy group at the end of the structure. And the second monomer is benzene 1,4-dicarboxylic acid. So both end structure have same functional groups, which are COOH. And when this monomer polymerize or react together, it will tend to produce ethane terephthalate. And both end different functional group, which is consists of OH structure and COOH structure. So as we can see here, the repeating units for polyester is right here, OCH2, CH2O, CO, and the benzene ring continue with the CO, right? So this repeating unit will keep producing or in a step growth, right? In a step growth manner to produce a polymer. And some advantages of the condensation polymerization are, first, it is cheap, light, and insoluble in water, which is tend to produce a low toxicity polymer. It has a strong covalent bond, which is unreactive and resistant to chemical, heat, or organic solvent. It also has high strength and electrical insulators, flexible, easily molded to form other shapes, sheets, rods, or tube. And we'll use the condensation polymerization in the production of the fiber, which is garments and clothes. Continue with the classification of polymer in the line structure. So a single polymer molecule may consist of hundreds to a million monomers and may have a linear branch, either crosslink or network structure. So the bond that hold the polymer structure is called as the covalent bond. So the atoms in the polymer molecule together will be held by the covalent bond, and secondary bond hold the groups of polymer chain together to form the polymeric material. Copolymer we use as a term that to describe the polymer that consists of two or more different types of the monomer. It means that the copolymer is actually the polymer that consists of more than one monomer. For example, if you have a styrene, butadiene, rubber, it consists of three monomer, which is monomer styrene, butadiene, and monomer styrene, butadiene. Consists of two monomer, which consists of styrene and butadiene structure to form styrene butadiene polymer. Okay, so polymer itself, it consists of many mers, right? So it consists of a long chain of the repeating chemical units. Polymer can be either linear, branch, hyperbranch polymer, crosslink polymer, and network polymer. So we look at the properties of the linear polymer. It is a polymer consisting of a single continuous chain of the repeat unit. For example of the linear polymer are polystyrene, polypropylene, which is contain of the monomer in a straight line. Actually, polystyrene is a good example of a linear amorphous thermoplastic, and it has a transition or glass transition temperature of 100 degrees C, and since it is amorphous, so the properties is clear, and some of the typical hard, clear, disposable drinking cups are polystyrene. So since there is no crystalline phases to melt, and above Tg they will soften and flow. And for semi-crystalline thermoplastic, it will tend to have both an amorphous and crystalline region. And the amount of the crystalline phase typically determine the physical and the mechanical properties. So the semi-crystalline polymer have a melting point or Tm and a Tg corresponding to the amorphous region. So for the branch chain means that a polymer that includes side chains of repeat unit connecting onto the main chain of repeat unit. You can see that at the linear chain it tends to have a branch structure attached to that linear. So we call it as a branch polymer. The branch polymer is quite hard which is quite hard to melt because this melting, this is the process we call as a thermoset polymer, because mostly branch polymer are thermoset polymer. So compared to the linear structure, if it is exposed to heat, it will break the bond between the long chain and allowing the chain to flow and pass each other. And these properties will allow the material to be remolded. And upon cooling, the bond between the long chain will be reformed. For example, polymers harden. Okay. For the branch polymer, since this shorter chain, if we can see here that attached to the linear chain, it can interfere with the efficient packing of the polymer, and branch polymer tend to be less dense than a similar linear polymer. So since the short chain do not bridge from one longer backbone to another, heat will typically break the bond between the branch polymer chain and allow the polymer to be a thermoplastic. Although there are some very complex branch polymer that resist this melting and thus break up. So branch polymer can be either thermoplastic or thermoset, depending on the structure of the branch polymer itself. Okay, for crosslink polymer, it is a polymer that includes interconnection between the chain. So the crosslink polymer, as we can see in the illustration, it is like a ladder. So the chain link from one backbone to another. So unlike linear polymer, which are held together by the weaker van der Waals forces, the crosslink polymer are tied together um, by weak van der Waals forces and by the covalent bonding. Okay. So in linear polymer, it is tied by the weak van der Waals. In the crosslink, it is tied together via covalent bond. So this much stronger bond make most crosslink polymer thermosetting polymer. With only a few exceptions to the rule, crosslink polymer that happen to break their crosslink at relatively low temperature. So for network polymer, it is a crosslink polymer that includes numerous interconnection between the chain. So it is more complex polymer that are heavily linked to form a complex network of three-dimensional linkage. So these polymers are nearly impossible to soften when heating without degrading the underlying polymer structure and are thus thermosetting polymer. So monomer do not have to be a single atom type, but when referring to a specific monomer, it is understood to be of the same composition structure. So the hyperbranch polymer is consists of constitution of repeating units, include a branch